So, based on this drawing and what we talked about on Friday, I think a reasonable question would be for you to tell me the acceleration of this system or the tension in the cable that's holding one of the masses. I think based on our discussion on Friday, that would be a reasonable question. But I also know, based on our discussion on Friday, that I'm probably only going to be able to get... Sorry, Siri, I wasn't interested. I'm probably only going to be able to get the correct answer from maybe 15% of you. Not because you're not smart kids, and not because you're not capable, but because through the course of doing those two questions, finding A or finding T, you're going to make a mistake somewhere in the middle of this. You're going to forget to take into account the direction of your vectors. You're going to put a negative sign where a positive sign should be. You're going to mix up the algebra. You're going to not do the substitution correctly. You're going to not remember that alpha, R, and A are all related. You're going to forget the idea that there's a moment of inertia. Do you know just how many things you have to remember how to do correctly to get this problem right? And it doesn't speak to whether you understand the nature of physics at all. It speaks directly to, are you a good enough bean counter to remember all the subtle details necessary to solve this? Now look, some of you can. And if I gave you 50 of them, after a while, all of you could. But there's probably not a chance this question's on the exam. If it is, it's probably multiple choice, which should really freak you out. But if it's on multiple choice, there's probably something about it that makes it very simple to solve. Some kind of proportionality or some kind of hint in the explanation. If they're going to offer this on the FRQs, they are very likely to ask you different questions. Questions that are going to speak to the qualitative nature of this problem, not the quantitative nature of this problem. So I want you to consider answering 3 questions. I'm going to give you the 3 questions right now. But understand, there's a larger question I will not seek the answer of. And that is, how is this system different now that there's mass in the pulley? I'm asking it this way because we've done this problem before. You might not remember, but first semester we did this problem. I can't fit the... There, now that there's mass in the pulley. We did this problem when there was no mass in the pulley first semester. It was an Atwood machine. Some of you, more like 50% of you or greater, were successful with this. You had to draw pictures like free body diagrams, showing that the weight for the 100 was greater than the weight for the 50. And then you had to draw, tension on both sides. You wanted to make sure the tension was greater on the 50 so it could accelerate upwards, but less on the 100 so it could accelerate downwards. These should be things that are familiar to you from your work from first semester. And although it has been a while, those things were relatively easy to remember. The problem is that this system isn't the same. We know from Friday's discussion that the pulley changes it when it has mass. So to answer question 1, you really need to consider 3 other questions whose answers really tell you the answer to question 1. The first one is simple. How does the shape of the pulley affect the answer? I'll say it again. How does the shape of the pulley affect the answer? I think I'm going to ask some of you guys to answer that question here in a minute. How does the shape of the pulley affect the answer? Are the tensions in the cables the same for each mass? are the tensions in the cables the same for each mass? And lastly, in what way does a change in the mass of the pulley affect the answer? In what way does a change in the mass of the pulley affect the answer? Now, here's what I'd like. I'm going to pick out 4 of you. It's 3 of you and a backup, and you're going to answer questions A, B, and C for me. I think you have the answers. They should be in your discussion from Friday. But I think more importantly, I'm looking for a qualitative answer. These are, in many ways, yes or no questions. But I want you to be able to provide reasonable explanations for your answer. So if you're going to use a vocabulary word, be careful. I might ask for its definition. So, I'm sorry to do this and put you on the spot. I know you guys hate that, but I tried to give you a chance to kind of talk with each other a little bit. So my first question, which was, how does the pulley's shape affect the answer? That's going to be answered actually by Jordan. So Jordan, could you please provide us with your table's explanation?
For A?
Yes, please.
Okay. So we said that the moment of inertia makes it easier to spin. Because you said that for smaller shapes, it's easier to spin and it more spread out. I'm really bad at explaining things.
I don't know that you did a bad job explaining it. I believe that many of the things you said in there are okay. How many of you would agree with the statement that she made or need it restated so you could hear it? Could you say just a little louder, please? Because I don't think I could do you justice.
So we said that the moment of inertia.
You guys heard that one that time?
Yeah.
Would anybody like to add anything to it? Yes, ma'am.
Maybe the shape, given that it has a radius, it adds, it causes a torque, adds angular acceleration to the system as opposed to being in machine.
All right, so I think there are several things that should be brought up here. I think all these things should be included. Now, here, what I mean by that is, if you say that the reason why the shape affects the answer is because it changes the moment of inertia of the pulley, everything about that statement is exactly true. But you didn't say how it affects it. And you didn't say what moment of inertia is. 2 things that largely need to be answered if you're going to say that the shape affects how it moves. So you should state something about if more of the mass is located towards the edges, the object will be more difficult to accelerate. That is a clear representation that you know what moment of inertia means. So not only are you using moment of inertia in the sentence, but you are defining it. And I know this sounds more like an English class than a physics class, but talk to anybody who took the exam last year and they will tell you they did more writing on this exam than the AP Lang exam, which seems pretty ridiculous to the physics teacher. The second thing, the idea of torque was brought up. I believe the idea of torque could plainly be used to introduce this idea as well, but torque relies on 2 things, force and torque arm length. So I think if you're going to bring up torque, your indication about the size has to do with how much torque could be applied by the string due to the change in torque arm length, which is what Ski said. I think that was great. Including how the torque is different due to the shape of the object is important. That shape being the length of the torque arm. That's how it's affected here. So, both of those I think have to be in there. So question B is about the tension in the cables. And hope your table is on deck for this one. Actually, it was on the line between you and Sophie, but the reason why I'm choosing your table is somebody else at Sophie's table was picked for the later on, and I'm trying to get different people from different tables. So since it was on the line, I defaulted to you. But now they know they're coming up in a few minutes. So, all right, go on. Tension.
We just said no because the 2 masses hanging off the pulley are different. So resulting in like different energies.
All right, did everybody hear that? Come on, broadcast from the diaphragm, thespian.
So they said because the masses hanging off of the pulley system are different, then it's going to be different tensions in the.
All right, did everybody hear that? Because she said that there's two things that she said, and I think both of them bear issue with your answer. First, her answer was the tensions are different. Now that's a point of fact that is being pronounced by you. You're saying they're different. So if this question was, are the two tensions the same or are they different? You have checked the box that says they are different. Now I want to point this out because oftentimes points are given not for the correct answer, but for your explanation of the correct answer. Meaning you can't get any points if you check the wrong box, but you don't necessarily get the points if you check the right box. The truth is, the two tensions are different. Her explanation is incorrect. Would anybody like to talk about the explanation as they see it? Okay, then allow me to help you a little bit. By saying they're different, that means that T1 and T2 are different. I'm labeling them so that T1 is on the left and T2 is on the right. Now, Hope's saying that because the boxes are of different masses, that would somehow change the tensions. That's not altogether incorrect, because there would be no tension if there weren't boxes hung on these strings. However, we've done this problem before. And when we did this problem before, the pulley was massless. If you guys remember, that doesn't work here. And it has to do with this incredibly important statement that net torque equals I alpha. Something we talked about last week. Does our pulley with mass have inertia? Yes or no? I'll ask the question again, and I'd like a verbal response. Does the pulley, because it has mass, does it have inertia? Yes. Then the only way it can accelerate is if the net torque isn't zero. If the tensions were the same, then the torque on either side would be the same, and the net torque would be zero. The reason the pulley turns is specifically because they're not the same. One torque on one side is greater than the torque on the other side. That's the only reason the system rotates, is because there's an unbalanced torque. So the way to answer this question is to indicate that you understand that an object that has inertia requires an unbalanced torque to accelerate. So by necessity, the tensions must be different. Believe it or not, what actually happens is the pulley uses some of the tension. That's why when you place the string over it, there's more tension on one side than the other, because some of it has to be used to move the pulley. Back to that, when it was a massless pulley, and we had two boxes hanging off of it, one that was smaller and one that was bigger, we set the upward tensions to be the same. Because we said it was one string placed around the top of the pulley. Because it was one string, the tension is the same everywhere. We said that the pulley simply redirected the force, changed its direction. But that the heavier box would have a weight that was greater than the tension, and the lighter box would have a weight that was less than the tension. That's how we did the problem first semester. That's what I described just a few minutes ago.